Júlio Cezar. He's from Brazil. So,
Thank you very much, Marcelo. So I'll try to be as quick as possible, but I just disclaim the competition is not fair, okay? So, but I'll try to do my best to keep your attention for the next 20 minutes or so. So first of all, for sure, I would like to thank the organizers for this invitation, but I would like, as one of the last of the speakers, I would like to really thank all of the other speakers because it has been a very fruitful week here. Okay, so our group is quite a newbie on this ferroelectric topological excitations, now I know, thing. So I think we learned a lot. But today I'm here not as, more as an advertiser than anything else, okay? So happily, along these days, quite a few among us showed some results that came from synchrotron use. So I'm here as a beamline responsible from one synchrotron in particular, our Brazilian synchrotron. And what I would like to show you is the potential that a specific range of the electromagnetic range, the soft X-rays have for study the kind of materials we have been talking about since Tuesday. So I will give a very brief introduction to the technique, but I'll not. The time is not enough to tell you how it works. But I hope I can show you what it can do. Okay, I'm going to follow some examples that I think can illustrate quite nicely the potential of a few techniques. I'm going to concentrate more on X-ray absorption and then on microscopy. But let's start. So to do spectroscopy, in general, you need a source. For X-ray absorption, spectroscopy is not different. You need a source. I hope I'll get early enough at the end of this section to tell more about the source. In our case, we need a source that produces X-rays, more specifically, something in the range between 200 and 1.5 kilo electron volts, so 200 electron volts and 1500 electron volts. These are the soft X-rays. They are soft, and that's important. If you can keep an eye, from the match now, keep an eye on me. Now, this is important. Soft X-rays, they are soft because they almost never transverse your sample. And this is important, and this was a drawback until recently, and now it became an advantage. I'm going to show you. So you have at the source, it's a synchrotron. I'm going to talk about I'm not going to show you what the synchrotron is. And you have your sample. The idea is to use the same technique that's very known in the optical range. That's the birefringence, or the dichroism. That's the property of the different interaction between radiation and matter, depending only on the polarization of the radiation. In our case, if you want to explore that, then another need for the source is that it must produce radiation with controllable polarization. Ideally, it should at least produce linear polarization horizontal, in the vertical, and circular polarization. With all these four possibilities, you can do a lot. And the most known dichroic technique in the soft X-ray range is the circular magnetic dichroism that I would like to explain quickly here. It's very simple. The measurement itself is quite simple. You measure one absorption spectra, in this case around the iron edge, with one helicity, it's in Portuguese here, so it's plus, one helicity is black and another helicity is red. For those of you that are not used with technique, the dichroic signal is the difference between both. And the interesting thing about this dichroic signal that with very simple sum rules until recently, and more in these days, more based on first principle calculations or multiplet calculations, from this signal you can extract very important information, magnetic information. Element selective magnetization. For each element, you can separate between spin and orbital contributions. So this is very important. It's very difficult to do that in general. But because we are in the soft X-rays, and because we interact a lot with the surface, because it doesn't penetrate a lot, and indeed, this surface sensitivity is more related with the technique, the detection technique we use that I'm going to mention in a moment. This dichroic technique is extremely sensitive to the few nanometers of your from your surface, deep in your surface. So it's very surface sensitive, okay? And these days, surfaces are very important. Interfaces are very important. So you can measure, due to this sensitivity, very small amounts of material. Hundreds parts in 1,000 of a monolayer. For example, you are sensible enough to get quantitative information. So to be just the technical part that I must clarify here is the following. So I told you the most used dichroic technique is when you illuminate your sample with circular polarization. And normally you are measuring magnetic properties, okay? A parenthesis here. You see the amperemeter connected to this sample. This represents the way we measure the absorption signal. Because the X-ray doesn't transmit through the sample, you have an indirect way of measuring the absorption. Normally, when you have the absorption phenomena, you have a decay that produces lots of electrons to the vacuum, and then you charge your sample. The moment you charge your sample, if it's conductor, from the ground, you have electrons coming up to balance this charge, and you can measure those electrons. This current is proportional to the absorption to a great extent, okay? It's not perfect, but normally it's admitted that's proportional to the absorption. But okay, so you are going to see these symbols very often to represent that the measurement was done checking the electron current needed to replace the electrons emitted. This is the total electron yield detection. You have the initial situation that I showed you. When you illuminate with circular polarization, applying a magnetic field along the X-ray beam, and this gives you that information that I mentioned on the previous slide, the magnetic moment, orbital and spin, and you can do element-sensitive hysteresis, for example, turning on the maximum of the dichroism and changing the magnetic field. You can make element-sensitive anisotropy, measuring dichroism for several angles in a thin layer, epitaxial layer, or single crystal. But there's another kind of dichroism, the linear dichroism. This is the most directed, it's the most usual, it's the most easy to understand. What X-ray absorption probes is the electronic structure of your material. If your electronic structure is anisotropic, your absorption will be anisotropic. So it will be different if you're for vertical or for horizontal polarization. And this anisotropy can be made, for example, if you apply a magnetic field perpendicular, in this case, to the X-ray beam. In this case, the horizontal will probe something different from the vertical. And this is the X-ray magnetic linear dichroism. It became very, very used because it's very sensitive, for example, very useful for antiferromagnetics, which normally are very difficult to probe. But you don't need a magnetic field to make any anisotropy. It can be a crystalline anisotropy, and you'll be sensitive to it also. And that's important. I'm going to show you in this example, I'm going to use this property. So what I'm going to do, I'm going to illustrate the potential. I hope you will notice how strong is this technique in this system, that it's a heterostructure of lanthanum manganite and strontium titanite. This was done in collaboration with people from Spain, and they grew very nicely heterostructures where they changed the number of unit lattices of the manganite, keeping always 2 lattices of strontium titanite. So I'm not going to enter in detail, but doing like that, they have samples with different magnetic and transport properties. Then the question was, what's the relationship between the macroscopic behavior and the atomic organization at the interface. Then we did the dichroism. Okay, the first approach was to do linear dichroism. Here I'm representing more or less this experimental setup. So we use a grazing incidence on the sample. In the real life, this is tilted. I represent here just to make it easier to relate with the results. But in our case, the samples always finish, they end with a top 2-unit cell strontium titanite, and then the manganite thickness is changed for several samples. I'm going to show you the results for the two extreme of the samples. So here, notice the following. When you have a vertical linear polarization, again, it's vertical here because the thing is rotated by 90 degrees. But vertical polarization, in our case, it probes mostly, the electric field of this polarization is probing the electrons that are in plane of the sample. On the contrary, the other polarization, to a great extent, its main projection is along the normal to the surface. So we tell that the X-rays, they have the searchlight behavior. You see things like that when you have the polarization vertical, or like that when you have the polarization in the horizontal. And the idea is to probe the difference between chemical bond in the perpendicular to the plane and in the plane. Results. So here is the measurement for a sample that has the thickest manganite layer. So 17 unit cells. We measure one polarization, another polarization. If you notice here in the zoom, there's a very small difference there. What you have when you do X-ray absorption is that you promote electrons from the core levels to the empty levels. The direction that has more empty levels has more absorption. So in this case, this signal, without any interpretation, says you have more empty states for the blue, the vertical. Thus, in this case, the 3D, so here's a transition from the 2p of manganese to the 3T, to the empty 3D states of the manganese. So you have more empty states on the vertical and more electrons, more population on the horizontal. So with this, you know that from the crystalline crystal field splitting, that you are populating more the Z² orbital than the X² Y² orbital. There's no need for getting anything qualitative like that. It's just looking, okay, to have it quantitative, but you can make it quantitative if you simulate. Then there's the other sample with the thinner manganite layer. So 3 unit cells. In this case, it inverted here. So what means that there was an inversion on the population. Instead of populating more on the Z² out of the plane, the electrons are populating more on the in plane, X and Y, X² minus Y². So this is a change that we can correlate it with the interaction, with modifications, with the ray structure of the orbitals at the interface. Okay, that was one information. Now, instead of linear, I'm going to measure with circular polarization. This is for the manganese again, and here you see the traditional circular dichroism. You have something like that, something that goes above in one edge, below in another. You see the different signal here in black, and the integral here in red. The sum rules for dichroism, they don't apply, they don't hold for manganese. Another go. They don't hold for manganese or titanium, as I'm going to show you. But qualitatively, you can have information. For example, here, the integral at the end of the spectra is directly proportional to the orbital moment. So here I know that the orbital moment in this case is completely quenched. It's 0. I don't know. There's no, if it wasn't 0 the integral, I could not tell you exactly how much it was, but as it's 0, I know that it's quenched. I cannot tell much about the spin moment. The only thing that with this value of the middle of the integral, I know that it's aligned with the field. This I know. Going on, instead of doing circular dichroism on the manganese, so this is for the two extreme samples. They have very similar behavior, 0 orbital moment. Doing the same for the titanium. The titanium is very tricky to measure dichroism, but we did. And here you see that the integral is not 0. So the orbital momentum at the titanium site is not quenched. I cannot tell you how much, except if we do some simulation here. And playing with these values of these integrals, I can tell you that in one case, the spin moment of the STO is anti-parallel to the manganite. On the other extreme, for the thinner, the spin moment of the STO is aligned with. Furthermore, this is strontium titanite, so it's D0. So you already know if there's a magnetic moment, there was some charge transfer here at the interface. So you need some charge electrons going to the titanite to, and you can see this, also this from the spectrum. So with that, I would like to show you how strong, how powerful this technique can be to give detailed information about the interfaces. With this information and with the good enough Kanamori-Anderson rules, you can make the complete scenario for this kind of material here, okay? So this is one thing. So I would be happy to discuss with any one of you. If, I know that's not clear. I didn't show you how we did that. I just show what we did. But I hope you understood that it's very powerful. With very standard measurements, you can have very deep information about your system. But you can do also microscopy with soft X-rays. You have some results here during this week also about photoemission microscopy. In this case, what you do, you shine your sample with X-rays and pick the electrons with half of a transmission microscope. So you have the column below the sample from that transmission microscope, put in front of your sample, and pick these electrons. So then you make a microscopy, but instead of the electrons coming from a gun, they are coming from they are created by the photoabsorption. And then you can do electron microscopy with the contrasts based on X-ray absorption techniques. So here, for example, is a topography of an arrangement of micro-island, permalloy islands, from people from here in Brazil that were studying these artificial spin glasses. I just want to show you that is a 100-micron field of view. But then you can do dichroism. And doing dichroism, then you can know, it is a slightly smaller field of view, but you know the direction of each island. This is standard. Any photoemission microscope does that. But you can have also, for the moment I told you, just mostly magnetic information. But you can also have information from ferroelectric materials. Indeed, the ferroelectric distortions on the BTO, for example, induce this anisotropy that I mentioned at the beginning that can be probed by linear dichroism. So doing linear dichroism, using the contrast based on linear dichroism, you can have image the domains, the ferroelectric domains. In this case, is a monocrystal of barium titanate, okay? What we did then, this is the work of our first PhD student, Caroline Mus. So what she did, she evaporated on the top of this barium titanate monocrystal a thin wedge of iron, simply iron, going up to 5 nanometers, more or less. If you measure the magnetic domain of iron, the iron edge, for the thick layer, you see the standard domains for a thin iron layer in the plane, randomly distributed. But when you measure in thicknesses smaller than 2 nanometers, you see an alignment of the magnetic domains with the ferroelectric domains. This was not the first time that it was saw. People did that also with Kerr microscopy. And, but here, in principle, now we can go to the resolution of this, in principle, I hope next year we can get there, go to something around 20 nanometers. And then you can investigate really domain walls in this case, hopefully. Okay? So this is my second example. So microscopy, and you can, in the same time, tune into the titanium, measure the ferroelectric, tune into the iron, measuring the linear polarization, titanium edge, ferroelectric domains, circular polarization, iron edge, magnetic domains. And we have measured a few regions. It's very interesting results here. I must tell you 2 words, this is going to be really quick, about these 2 techniques here. Remember this name, resonant inelastic X-ray scattering. You are going to hear about that in the future, if you didn't hear yet. This, I used to say that it's absorption with steroids, okay? Because you have much more information from this technique than you get from absorption itself. But these 2, they allow us to have really a fine picture of the electronic structure. And how this is done. So ARPES, Eduardo Abramov, that was here, showed some examples, is a kind of XPS that where you, besides having the energy of the photoelectrons, you have the momentum of these photoelectrons. Having momentum and energy, you can build the dispersion curves. And that's exactly what you measure. It's a snapshot of your samples. It's a nightmare to prepare the sample, but when it works, it's beautiful, okay? So far, the fact that you have ferroelectrics are intrinsically isolating. They are not very suited for this kind of measurement, XPS in general. But these days, where you have very nice thin films, epitaxial films of these ferroelectrics, then it starts to become feasible to measure ARPs on ferroelectrics. Indeed, that's our project. It's one of the projects in our group. Okay. This is for the ARPs. I'm not going to enter in details, but it's very powerful. This is quite new. It's the RIX, resonant inelastic X-ray scattering. When you have absorption, you promote electron from the core to the conduction band. During the decay, normally you have electrons, the electrons that we measure in the total electron yield. But you also have photons, the fluorescence photons. If you have a good analyzer, a good spectrometer for these fluorescence photons, you can have a fine picture of what you have here on the conduction band. Today, people are able to study excitations that are close here to the phonons. We are not very good with phonons still with X-rays. Neutrons are much better for phonons. The trouble that with neutrons you need lots of material. So now with X-rays, you can do a very thin layer of superconductor and have this kind of dispersion. This has been done recently. It has been a race for better and better resolution. So this is the kind of result you can get. This was is the dispersion of the bimagnons in the parent superconductor, the calcium cuprate, the parent compound of some superconductors. So this is the kind of dispersion that you cannot have by other means, okay? To finish, I told you that you need a source. So far, our source still is a synchrotron. For those that don't know, we have here, exactly on the tropic, 20 year that has been open for users 20 years ago, a synchrotron. That's quite small machine. And this year is its last year of life, okay? We are closing it this year, and hopefully next year we are going to be inviting the new synchrotron, okay? For you to have an idea, this building here is that one. It almost fits here in the middle. This is merchandising, okay? This is a 4th generation machine in the sense that it has a very small electron beam that we call emittance. This allows naturally to have very small beams. And for us that we are going to do, for example, photoemission microscopy, this is going to be really a change of life. what takes today around 4 hours to have a good image is going to take 4 seconds on the next. The time resolution here is going to be much better, so we can do some dynamics, not as good as some femto lasers or free electron lasers, but we can still do things down to tens of picoseconds. So this is our new synthesis. Is going to be, the civil works are going to finish around this year. There's the Linux already installed. And in this synchrotron, at the first phase, we hope to have 2 soft X-ray beam lines, a third one in more 2 years. And this, we are going to have RICs and ARPs in one beam line, PIN and another kind of scattering, soft X-ray scattering in another beam line, and a lot of X-ray absorption and photo emission in the other here, okay? So I invite you all to have a look on that. We are going to have several nano beam lines for nano diffraction, and we are planning to have really what is a state of the art, okay? So, and the plan is going on the schedule and on the budget, believe me. It's amazing, but it's so we hope to open for users, a few beam lines open for users until the end of next year, okay? So with that, I'm going to finish. I just want to tell you this thing that we are investing a lot of in-situ sample preparation for these beam lines. We have a system that it's a big vacuum tunnel with several chambers. And in this system, we have molecular beam epitaxy with several evaporants, several possibilities, pulsed laser deposition, and an organic molecule evaporation system. So we are really able to grow very nice samples after structures. The sample that Flavia showed yesterday was grown on in this PLD and transferred under vacuum to all these facilities, okay? So we are investing a lot on that to be able to do quite well in situ characterization. So my final comments, I cannot avoid thanking all our team. Really, they are doing, I'm very proud of saying that we are doing pretty well recently. And if you want to keep some message to take home, soft X-ray interfaces, due to this surface sensitivity, they are really a perfect match, okay? They're very powerful. So if you want to study interfaces and surface mostly, think about soft X-ray. Of course, it's not a panacea. It doesn't solve everything, but it's quite well complementary to other techniques. Normally, from soft X-ray, you get detailed electronic structure information. Now, with photo emission microscopy, and people showed here also some scanning transmission microscopy in the soft X-rays that are very powerful too. We are not going to have a Stixen right now, but we plan to have in the future. You can have a spatial resolution with image-based on the several contrasts that X-ray absorption provides. Chemical, magnetic, why not the ferroelectric? So this you can use as contrast for spatial resolution down to 20 nanometers, I would say, if we imagine have a good beam line. And it's something that I didn't mention, but given the wavelength of the soft X-rays, you can have nice information about mesoscale structural information doing soft X-ray diffraction. So I thank you for your patience, and that's all.